Good morning, everyone, and welcome to the KETIV Autodesk Virtual Academy, our once-a-week learning session for any and all Autodesk products. Today we have a really exciting session for you. As you can see on the screen, Autodesk Simulation CFD, Computational Fluid Dynamics. This brings me back to my college days when I was stuck in a lab for hours on end working on simulation. So with that, today we have special guest James Neville, and just to give you a little background on James, James is a sim expert with a specialty in CFD. Began working in the field about 2003 and has a lot of experience among a wide range of sectors. He graduated as a mechanical engineer, like myself, from Virginia Tech and began his career at Blue Ridge Numerics, where he focused a lot on customer success through consulting services. And now he serves as a global subject matter expert at Autodesk for CFD itself. James lives in Pittsburgh, Pennsylvania, so a little east of us here in sunny Brea, California. But with that, I'm going to go ahead and pass it on to James. So, got the floor.
Thanks, Nigel. Appreciate the time. Glad to be here for you guys. First things first, what I want to do is I want to go over the Autodesk Simulation portfolio before digging in specifically to Autodesk CFD. We do have a wide range of simulation products in our simulation portfolio, ranging from structural mechanics for both small scale items all the way up to large architectural items. And customers typically use those sort of technologies to analyze stress and strain and displacements and answering the questions of whether or not something will break or bend or fail. The tool set that I'd like to talk about specifically today, Autodesk CFD, falls into the sort of the middle bucket there on the screen, flow and thermal analysis. We'll dig into more of that in a second. We also have some more advanced processes, both on the plastic injection molding side and the composite structural side as well. But specifically today, what I'd like to talk about is Autodesk CFD, Computational Fluid Dynamics, and that is our fluid flow and thermal analysis tool. So what is Autodesk CFD? So CFD does stand for Computational Fluid Dynamics, and that is a tool that is designed to allow designers and engineers to analyze their fluid flow or heat transfer problems. Our users typically take their geometry from CAD. So if you have a 3D solid or a 2D shape, you can bring that into CFD. We do include a tool set called Sim Studio tools with all of our simulation products. And that is sort of a direct modeling tool that allows users to push and pull and massage the geometry a little bit. You can do the same thing in most CAD packages, but Sim Studio tools has specific functionality built into it that's geared, very focused towards simulation guys. So, whether it's the ability to remove very small features or close off small holes, there's a lot of neat functionality in there to help facilitate getting that model into a simulation environment. We do have a full mesh auto-sizing and results adaptation optimization in the program. And what that means really is that whether you are a novice user just out of school, or maybe you're just picking up the tool for the first time, or maybe you've been using the tool for 10 or 15 years, you have the ability to get the same results with the same fidelity based on the automation that we built into the tool. So it's really handy to be able to compare multiple data sets from different users and have confidence that you can have a nice design comparison between those results. You can take the thermal stress and pressure loads from CFD into any mechanical structural analysis program, whether that's our own NASTRAM programs or bringing that onto maybe a third-party deck. We do have that built into the tool set. The environment, which we'll look at here in a second, the interface, is really geared towards looking at more than one design or more than one scenario at a time. So what that means is that instead of just using the tool to analyze just one simulation here or one simulation there, it's really geared more towards looking at more than one simulation. So giving you sort of a back-to-back comparison between multiple design iterations. Typically, in early stages of product development processes, there's many avenues or many routes that you can take. And the interface is really designed to allow you to explore all those different design options. We do have full parallel cloud solving built into the software. So if you like, you can launch your jobs to the cloud and take advantage of the infinite cloud computing available through Amazon. And like I said earlier, it doesn't really matter where your CAD comes from, whether it's PTC Creo or SolidWorks or Inventor. It just doesn't matter. We are CAD neutral, so you can bring in any file format into CFD and solve it. So I just want to briefly go over some of the areas where our customers have success with our tool. It is a general purpose tool set. So if you build it in CAD, you can bring it into CFD. And these are just a small example of some of the larger industries where our customers have success using CFD. So you have electronics cooling, customers are trying to get the heat out, right? So you have components on boards, fans moving flow through heat sinks, and ultimately we're trying to optimize the airflow inside that system and make sure that the thermals are behaving appropriately and we're getting the heat out efficiently. Moving up to a larger scale, you have data centers, which might have a large number of electronics in them in the racks, and we're looking at simulating and evaluating how that airflow moves inside and around the crack units that are in the next room, and how that air is distributed through the diffusers and the supplies, and ultimately we want to make sure that our cooling system is appropriate for the amount of power that we're dissipating inside that data center. Lighting, sort of a subset of electronics, but we're very concerned with the amount of heat that will build up inside the junction area inside an LED to make sure we have optimal performance, and light output is efficiently managed, and the energy is dissipated through the heat sinks. Lighting is a great application for CFD. I think machinery and valves is probably the sort of the bread and butter typically for most CFD programs. This is a sort of a broad area, but anything where you have fluid flow or air moving through a valve or a pump or something like that, you can simulate that in CFD without actually having to build it. And then on the large scale side, the architectural side, this is really getting into like room scale, building scale, or maybe even the scale of the airflow around the building. So really broad range of applications where CFD can help our customers. This is only just a small example of some of those. So before I jump into software, I just want to give a brief overview of the tool just one more time. So Autodesk CFD is a full-featured fluid flow and heat transfer analysis program. There's all of the standard laminar, turbulent, incompressible, compressible technologies, along with some more advanced options to allow users to get into more high-speed flows or time varying mixing calculations, solar loading, radiation, current and voltage. And with that, I think I'd like to go ahead and move over into SimStudio tools and give you guys an idea of what the tools actually look like. So on the left, I've got design 1, that's the one we just looked at, and on the right, that is design 2. So this is an apples to apples comparison. The only change is on the lower right-hand, sort of the front portion of the electronics enclosure, this gaming system. I have moved the slots, moved those vents. So the goal here is to try to get the flow to go through the heat sink, right? That's where I want to get my performance. I want to get the heat out in that area. So by moving these vents towards the front, I'm trying to sort of throw the flow or let it be pulled more easily through the front end here. And I think it does work. You can see that we're not getting quite as high of a velocity around the side here, but very clearly you can tell there's definitely some flow that is bypassing the heat sink there. So what I want to do next is maybe look at another design. I actually have 4 here, but let's go ahead and compare designs 2 and 3 at this stage. So I'm going to have design 2 on the left and design 3 on the right. Go full screen for you guys again. So what I've done with design 3 is it's the vents are in the same location, but if you look on the right, there is a shroud in place. So there is a sort of a focusing shroud on the back end of the heat sink. You can sort of see the outline here. Maybe I'll do I've got a couple better images here in 3D that'll better illustrate this. But in effect, what this does is it focuses all of the flow that's being pulled from those fans. All that flow must come from the heat sink. So literally, these are like guides that are keeping all of the flow through the heat sink, and you can dramatically see a difference here. So if I zoom in just in this area, check out the velocity difference inside the heat sink fins themselves. It's night and day. I mean, you're looking at 2-3 times more velocity than the heat sink fin. So we're going to get vastly better performance, at least from a flow perspective. That usually translates over into the thermal performance as well, but we'll take a look at that in a second. But you can see that the velocity through this area is just, it is night and day, like I said earlier. We've largely dropped our bypassing flow by a large margin around the outside of the heat sink. So this shroud is really, our best performing design, but just giving you guys an idea of how you compare these back to back. Let's take a look at some thermal stuff while we're here. now what we're going to do, we're going to look at, let's do design 2 and 3 again. Let's get top-down view. So let me just get the view oriented for you guys. So again, on the left, we have design 2, and that's the one without the shroud. And design 3 on the right does have the shroud in place. And what we're looking at now on this plane, we're looking at temperatures instead of velocities. So instead of just looking at, the velocity magnitude on this plane, now we're showing the actual, magnitude of the temperatures. And you can clearly see that this heat sink zone is quite a bit warmer on the left than it is on the right. And we're getting better, overall better performance through the system with this updated design. So one thing I like to show on these planes are velocity vectors. So instead of just looking at solid data or having it look like a solid plane, you have the ability to show the directionality of the flow as well. So as you zoom in here, you get this sort of 3D view, and I'll rotate this real slowly so it shows up on the web okay, but you get this 3D view of how the flow is moving. So not only are you looking at the velocity magnitude, but also the directionality of the flow, which I think is important because it lets you know a little bit more information about how the system actually works. There you get a pretty good idea of what that shroud looks like in the back there. But you can clearly see how that flow now enters from that vent, that inlet vent, and that flow enters now appropriately as it goes through the heat sink fan, and we get very low velocity. These vectors over here are blue, so they're effectively not moving. They do have some directionality to them, but the velocity is very, very, very low, like less than 1/10 of a meter per second. So very, very slow over there. Much higher velocities through the core region in the heat sink. A couple more things to look at here, and then we'll dig into the setup on this model and give you guys a full understanding of what it's like to set this one up and then dissect the result in real time. I do want to look at the heat flux values. So for those guys concerned about thermal performance, I like to look at heat flux because it gives a good indication of how the particular design is performing. You can see I'm just cycling through the 4 designs here. I do like to use a split screen view because it helps to illustrate the design comparison that we have built into Autodesk CFD. But what I'm going to show here is the actual heat flux here in the comparison between design 2 on the left and design 3 on the right. So the heat flux is the amount of heat transfer occurring at the surface, very critical for anyone who's concerned with heat transfer or electronics cooling. And just take a look at this heat sink performance. So on the left, you've got design 2, and you can see there's definitely a lot of heat transfer at the front end, the front edge of these cooling fins, but you get dramatically better performance with design 3 by having that shroud in place. So really by focusing that heat sink shroud and maximizing the performance through there, we're getting a lot better design there. And I think if you guys have ever cracked open a desktop computer, or if you have the ability to look inside one of your laptops or just look online, you can find a lot of pictures there. Most customers who leverage CFD have shrouds in place or some sort of a flow control device to maximize the performance of these heat sinks. So we looked at a lot of visual comparative data. Let's take a look at some quantitative data as well. So I'm just going to focus. There are chips underneath these heat sinks. Let's take a look at the data from the CPU and the GPU. So electronic customers typically care about the junction temperature for these components, and I'm going to look at the junction temperature of the CPU. That's sort of like the maximum. That's a critical area for the CPU itself. So let's adjust the scale here so for better illustration. So this is a back-to-back plot of the junction temperature from these 4 designs. So you've got design 1 and 2, which are largely the same. We've just moved the slots a little bit there on the left. And I've got a reference line of 90 degrees there, you can see. But designs 1 and 2 on the left, designs 3 here. And then design 4 was sort of an experimental heat sink that we did with an elliptical fin that doesn't perform very well, so I usually don't share that one. But you see that just by going from designs 1 and 2 to 3, we get a dramatic drop in junction temperature there, 3-4 degrees. It's enough to get it under that maximum allowable reference temperature of 90 degrees. Largely no change in performance. You go from 90.7 to 90.7 with designs 1 and 2, but you really drop down there with design 3. So, you have the ability to do some really nice results interaction and interrogation in CFD, but it's all based on data. And this data is shown here, and it's allowing you to dig in and get some quantifiable metrics when you guys are making your design decisions up front in your product development process. Take a look at the fan. So we do have those two fans that are pulling flow through the system. And the way we set up fans in CFD, the way we set them up is with fan curves. And those fan curves are provided by the manufacturer, and you can input the fan curve directly into CFD. And fans are typically rated for a certain flow rate, but they don't actually perform at that flow rate. And oftentimes it's 30, 40, 50, 60% of that maximum flow rate. So CFD has the ability to show what the actual resultant flow rate will be from these fans. So check this out. You've got design 1 and 2 here, columns 1 and 2, and then 3 and 4 both have that shroud in place. And what you notice is that you're actually getting a lot less flow through those fans, and ultimately less flow through the system with designs 3 and 4. And that might seem backwards. How are we getting better, visually better airflow, and visually and quantifiably better thermal performance with less airflow? But it's just that's how it works. Even though the system is moving less cooling air through the system, it's more efficiently moving. So this is just giving you an idea of what that actual operating point is going to be and where you'll fall on the actual fan curve. And if you look at the pressure across the fan, this is sort of a gauge of the restriction, or how hard the fan is going to be working to move that airflow. Oops, I must get a little too aggressive there. A little not aggressive enough. You can clearly see that the pressure drop across the fan is quite a bit higher, maybe not quite a bit, but measurably higher with design 3 and design 4. So it's this sort of data that helps our customers properly size those fans, make sure they have the appropriate amount of airflow moving through the system, and ultimately build have the best design before they go to 3D print any of their parts or cut some metal. The last thing I want to show here, let's take a look at the data as the airflow comes out of the heatsink, and this one shows really, really well. Make this graph nice and large for you guys. So all 4 of the designs are plotted on this graph, and we're looking at velocity first, but this is sort of just a left to right, connect the dots, graph the data along this line, XY plot that we have. And what you're looking at here is the velocity as the air comes out of the heatsink fins. So it's a really good measure of the performance of the heatsink in terms of how the airflow is moving around inside the enclosure. So the blue line and the lighter orange line, that's design 1 and design 2, and you can see that they're at the bottom here. They're in the less than 1 meter per second on average range. You can see them down there, and no wonder that the performance suffers, because the heat sinks really aren't performing as well as they can. Take a look at design 3 and 4, dramatically higher. I think I said 2 or 3 times higher performance, but it might be more like 4 or 5 times with design 3, higher airflow there. You can see just much better velocity performance, both at any point along the line, on the backside of these heat sinks, you're getting a lot better velocity there. Take a look at temperature on that same line. So this is converse to what I just said. Now with looking at temperatures, the amount of heat that's allowed to build up in that heat sink with design 1 and 2 without the shroud is significantly higher when compared to design 3 and 4. Just another graphical illustration. This is sort of graphical and quantifiable, but just giving you an idea of some of the result interrogation techniques that you can use while leveraging CFD to improve your product design.
Definitely. And just a quick question on this, James. How easy is it to export some of these results into like a report, something that you can send via email to somebody else?
Great, yeah, awesome question. So all of the data that I just showed, all of the quantifiable data, you can export in Excel-style spreadsheets, CSV files, and text files that can be exported and then brought into Excel for data further analysis or regression or what have you. And then, of course, all of the graphical stuff that I've shown, you can either export those as images or videos, or something I'll show here in a second, which we call a dynamic image, which can then be embedded in PowerPoint, and basically allows you to rotate the results around without having, basically you can look at a result image without having access to the CFD tool itself. So you could send that to a customer or a prospect, or maybe a manager who's never going to install CFD on their Ultrabook. They could then look at results in real time, just like you are or I am on my screen right now.
Definitely, thank you.
Sure thing. So I am, let's see, I'm in the setup ribbon here, and really just a brief overview of the interface here. There's a setup ribbon and a results ribbon. I'm not going to dig too much into here because I know this is a sort of a relatively high-level presentation, but the setup ribbon allows you to set up things like materials, boundary conditions, automate your mesh size, all that good stuff. And then the results ribbon allows you to do all the image creation and to basically process your data and create the sort of imagery that I just showed you. So you've got materials, boundary conditions, and mesh sizing. Those are the big ones here. So as I move over, you can see which parts are which. I'm going to make this one transparent so you can see that one there. That's the airspace. Cool thing, that's actually created for you when you launch in from CAD. CFD will automatically create the airspace for you, so you don't have to put in extra cycles on the CAD side to create that. Just to give you an idea of what some of these materials are, you've got aluminum heat sinks. There's your two chips there, fans in the back. As you assign your materials, they are summed up here on the left, very much like a CAD feature tree. It does read your direct CAD as well. So if you have materials assigned in CAD, we can read what those materials are, and CFD will automatically assign them when you get in. So you can actually skip the material step altogether with a couple rules that you create. Boundary conditions, these are just fancy terms for inlets and outlets. So you can see on this inlet here, I've got zero pressure, and that's just an atmospheric condition there. I also have zero pressure on the back end. So there's a full gamut of boundary conditions here that allow you to properly set up geometry. Basically, for electronics or for most analyses, it's just where does the flow come in, where does the flow leave? Does anything generate heat? You can see that I've got 60 watts on my CPU, maybe 35 watts on my GPU, and a couple other components that are also generating heat. And again, like the materials, as you assign them, these boundary conditions are summed up. So you can either directly pick the appropriate surface or part there in the tree, or you can just manually select it in the graphical window. Last thing here, mesh size. So again, we do a fully automated mesh sizer. I briefly touched on this in the presentation earlier, but just in a nutshell, what this does, it looks at your geometry and will automatically add more detail where you need it, and it will take away detail where you don't. And then result adaptation, when you solve, ensures that that mesh is appropriate for your particular setup. So it is completely hands-off. You can definitely get your hands dirty and dig in and make changes. And some guys who have simulation experience like to do that. It makes them more comfortable. But really, we put a lot of effort into the automation of this process. And I think you'll find that the AutoSizer works really, really well. And if you want to dig in and customize your mesh, you definitely can. But almost all of our users rely on automatic meshing. So let's dissect this one just a little bit here, just a couple minutes of interactive results, and then we'll turn it over to some Q&A. I'm just going to slap a results plane on here.
And then James, on those same lines of like refining your mesh and everything,
Sure.
As we all know, the more refined your mesh is, the longer one of these simulations is going to take. Is it the same case as it was maybe 5 to 10 years ago when you needed some kind of supercomputer to do all of this, or is it a lot more feasible to do very fine meshes on your general workstation laptop or desktop workstations?
Great question. That's a tough one to ask, and I think it goes along the lines with a question that we get a lot from customers. That is, what sort of hardware do I need to run this? And that answer changes almost daily. With the rate at which computers are changing and evolving and performance is increasing. But in general, CFD will run on any machine. And the power that you have these days, the amount of RAM that you can get in even a very small laptop, the amount of power that CPU inside that laptop has, you can run almost anything on almost any computer. Really, the more CPU you have, or the more CPU, the more cores, the more number of actual CPUs you have, the faster the simulation will run. Period. Right. So it will CFD will utilize whatever you can throw at it, but it doesn't need a lot to run. And then as far as like the size of the model that you can run, it's really dictated by the amount of RAM in your machine. But I would say that most even low-end engineering grade laptops and desktop workstations are perfectly acceptable for simulation runtimes today. So something like this, or something even a lot more complex, I mean, you're looking at anywhere from 30-minute runs to several hours for a single simulation. And that doesn't even get into sort of performance increases you can see with cloud utilization. So let's say I've got these 3 or 4, as it were, designs in my design study, and I want to run all of them. I think each one of these takes about 45 minutes to run on my laptop. I can solve all of these in parallel on the cloud, and they'll all solve in 30 to 45 minutes and come back, right? So you can save yourself a lot of time, especially if you have a lot of different design configurations, or a whole range of flow rates you want to test, or power dissipations, or whatever parameter you guys are looking at. Leveraging the cloud allows you to realistically run so much more than you could previously, because typically on one machine, one analysis is going to eat up all of your resources. So you can really only run one simulation at a time, where the cloud gives you just almost absurdly parallel computing capabilities.
Definitely, yeah, it's a lot, and even utilizing a tool like this, just even regardless if it takes a couple hours to do your simulation, a couple hour simulation is still a lot faster than creating a physical prototype, throwing some temperature nodes on it, and then actually doing a real life test. So definitely leverage the tools while you can.
Very good question. Yep. So I'm just going to slice and dice the model here for just maybe a minute or two here, and then we'll definitely open up for final Q&A. But on these planes, you can do so much stuff. There's we can measure data. Your mouse functions as a virtual thermocouple or a pitot-static tube to measure pressures or velocities like an anemometer. In the lower left-hand corner of my screen, I assume you guys can see that there's an XYZ location and also a value. So anywhere I move my mouse, whether it's on a solid or on these planes, you get data. There's hard data there. And you can very quickly change what you show on these planes. Right now I'm showing temperature. Maybe I want to look at velocity instead. So there you are looking at velocity. And maybe I want to come in here and I don't just want to look at the solids. I want to look at the vectors as well. It's very easy to just right-click or left-click and change whatever you're showing here. If you want to get data across a specific region, maybe I'm looking at how that flow looks like. The flow is blocked a little bit by some of these transistor components inside this shroud. Maybe I want to get a feel for that and plot the data across a couple points here. Here's my connect the dots, plot that data. You can see the red line that I drew there in the back, and there's the data along that plot, right? So you can export this data. You can change it. Maybe I want to look at the temperature instead of just the velocity. So it's really interactive. It's definitely fun to use, but the results visualization are really impactful here in CFD. Let's do a couple things here. Let's take a look at some particle traces, something I haven't shown yet. Just going to slap some particle traces on each side here. One from that side, and maybe I'll do the same thing over here. Boom, so there you go. So I just dropped some particle traces into the system, and these particles are awesome because they function as sort of like virtual dust particles that you can just throw into the air, throw into fluid, and then model where they go. And they don't always go where you expect them to go. Flow does take the path of least resistance, and clearly here that path of least resistance is even with my best performance design that I'm looking at now, design 3. The path of least resistance for a lot of these particles is not through the heatsink. So there's definitely room for improvement. You can see a little vortex thingamajig going on here, some sort of flow that's developed over the top of the heatsink. But it's pretty clear how the flow moves in and around the system, and how the heat moves around the system once you start looking at some of these results interrogation techniques. So I can definitely go and show off some of the additional results interrogation and design comparisons, but I just want to pause here for a second. I think as far as touching on all the bigger items that I wanted to get through to you guys today, I've done that. But just in summary, any CAD, any solid or 2D geometry can be launched into CFD. We have some specific tool sets that are designed to allow engineers to prepare their geometry to get the best performance and really focus your simulation efforts on what you really care about. You have specific tool sets and SimStudio tools that allow you to do that. The setup, the meshing, the results adaptation, that's all automated for you guys. So there's a lot of really nice automation features within CFD. And then naturally, once you have results, you can compare them amongst multiple designs, and hopefully that's come through really well here. Yeah, I want to open it up to some Q&A here now that we're at the sort of end of the presentation, and see if you guys have any questions.
Definitely, and thank you, James. It looks like we've got a couple of questions that came in. First off, I just want to mention we do have a couple of future events. If you want to jump to the slide before this, James.
Surely.
Real quick. So next week, October 27th, that is Thursday, we are doing a Vault Care 101 workshop where you can come to KETIV Technologies here in Brea, California, and kind of go over with us, some of the best practices for your vault. The last thing anyone wants is, a big catastrophic and for you to lose all of your data. Definitely the scariest thing possible. And there's things you can do to avoid such things. Obviously, you can't predict server failures all the time, but if in an event something like that does happen, there are ways to make sure that you do have your data backed up somewhere. And best practice to kind of avoid all of that in the first place. Again, December 6th, we have an Inventor Gunslinger event hosted by us and Autodesk, where you can get a first look at the Inventor Alpha or / Beta, depending on where they're at in that process. It's a full-day workshop where you can work in the tools for next year, kind of give your feedback to product managers, the developers themselves in regards to what you like, what you don't like necessarily from some of the added features in the new software, and maybe get those implemented for the next year. So I do suggest coming to those things. I'll go ahead and put the Vault Care 101 workshop link in the description. Again, if you're interested in the December 6th event, please let us know in the survey. There's a question for that specifically, and we'll make sure you get invited to that. So on to Q&A. So if you want to jump to the next slide here, James. So there's a couple things here. First off, I've got a question here from David, pretty high level. Can you touch on the differences between CFD, CFD Advanced, and CFD Emotion? James, you want to take that one?
Sure, great question. So there are 3 levels of CFD, 3 levels of the solver. Basic, I think we just call it CFD, and then Advanced and Motion. So what Advanced, I think it makes no sense to talk about Advanced and Motion. So what Advanced adds over Basic is it adds transient flows. So the ability to do a time-varying simulation. So you want to model how a room heats up over time, or maybe your flow rate increases over time. Through a valve system or something like that, gives you the ability to do, transient flows, compressible flows as well. So if you're looking at very high pressure drops through systems or very, very high speed flows, you'll need a compressible solver to adequately simulate the physics that are involved. If you're looking at like mock flows or solar radiation. So there's a specific sort of higher level physics that are included with the advanced module. And then the motion module has everything that the base and advanced modules have, plus the ability to have moving solids. That would be like rotating machinery like a turbocharger or a compressor, fans, maybe a door opening and closing, a valve opening and shutting, basically the ability to move a solid or have a solid move through the flow, if you will. I'll say this, something like 80 to 85% of our users have the advanced package because it includes most analysis types that they would need to do their day-to-day simulation work.
Definitely, yeah. All right, then. We've got a couple more questions here. One from Patrick. It's from Patrick. We are experimenting, with a flow-driven motion of a solid part, for example, a spring and poppet valve, so mushroom valves, and we're in need of more resources in this area. Can you help us? Do you know if there are any demos out there or videos for things like that, James?
We do. So there's good question. There is a very active online forum, which we have a lot of users. They'll submit their questions or comments there on the online forum. But really, the best I'll put in a plug for support here, shameless plug. But the best way to get immediate assistance with something is to case. I know that might sound like a cop-out answer or anything, but I came from support initially. That was my first role at Blue Ridge Numerics, and I was supporting actually this technology, the CFD technology that I showed earlier. And our support engineers are not just guys that are waiting by a phone to do an installation and licensing question, right? Or say like, yeah, my graphics card's behaving weirdly. Can you help me out here? gladly they will help you do that sort of troubleshooting. But where you get the value out of dealing with support is to leverage their industrial experience. So these guys have seen literally everything. You'll be hard pressed to surprise them with an analysis type that they haven't seen already. They have so much information. They're also very active on our support forums and our user forums. But my suggestion, let's say you're starting up a new analysis type, like you might have done a lot of steady state valves, valves that aren't moving, and then you're stepping up your game and you're doing some moving solids now. You have a flow driven, a spring loaded valve. That's it's still a valve, but it's you're adding in some more physics. There's some specific considerations both on like the CAD preparation side and the analysis setup side that you might want to know. Your best idea, beyond looking at the help system, which is relatively complete, and also I think has an example of a flow-driven valve in there, which is pretty good. Your best bet is to call up support or submit a case, and they'll call you and just say like, hey, I've already mastered these sort of skills in steady state non-moving valves, but I'm moving on to some more advanced stuff. Can you help me out? And they will give you all the information that you'll need and point you in the right direction if there's material that's already created, so that you'll be the most successful. And it'll give you some industrial background experience with it as well, to really get you off to the races as soon as possible.
Definitely, for sure. Thank you for that. Again, like I mentioned, I'm going to put the Vault Workshop link in the chat real quick for everyone if you guys are interested. And along the lines of support, if you're having if you don't know how to get to Autodesk support, go ahead and email us at questions@ketiv.com or call us at that number there. And you can talk to anyone on our Lifeline team. If you need to get directly to Autodesk support for something like some super high-level CFD question, if you want to talk to some of those experts over Autodesk, please let us know. We can get you connected. It's not a huge issue on our end. We can be that middleman to get you to the promised land, I guess. Let's see here. We've got a question from Paul Bannister. What has 2017 added over 2016? Anything specific?
Yeah, there's too many things to get into in this phone call, but there are some performance improvements both on the solver side and the interface side. We've added a couple new material models, some simplified material devices specific to maybe electronics cooling customers and architectural engineering customers. So there is a much more advanced humidity model. So when you're doing HVAC simulation in a large building space, now the humidity model allows you to add water or remove water or simulate. I think there's like 6 or 7 different types of HVAC scenarios that allow you to simulate. Basically, give you all the information you need to right size your HVAC system. There's a scalable solver which allows you to run on massively parallel computing infrastructure, which admittedly most users don't have access to today, but we're laying the sort of the foundation groundwork for the ability or users to have the ability to run their simulations much faster, many orders of magnitude faster than what's possible today, also with smaller footprint. So there's a lot of performance improvement technology in 2017 versus 2016.
Definitely, for sure, and yeah, just to answer everyone's question, or to answer that question a little further, Paul, they're always improving the software and everything, even things like operating system compatibility. That's a big one too. I understand, as well as just things to make the experience better on the customer end of things, which is also runs along the line of the event that we're doing in December. I do suggest if you are able to go to that and you are an Inventor user, to go ahead and try to make it out to that, because definitely nothing better than getting the customer's point of view in regards to making the product better for you in the end. I think that's it for questions. What I'll do is I'll give you guys another 30 seconds or so to go ahead and type any of those out. Just let you know if you do have any more questions that might be specific to your workflow or any other questions that might not be CFD related. Go ahead and ask them now, or go ahead and submit them in the survey at the end, and we'll be able to get someone to follow up with you. I'm going to answer any questions you have. I know that a lot of these webcasts do people do come with some specific questions that might not be related to the webcast itself, but definitely more than happy to follow up with anyone with any Autodesk related question afterwards, whether it's licensing, troubleshooting your product, running into error messages, things like that. We're more than happy to help. So with that, I think that's everything. Yeah, so again, James, I'd like to thank you for being here today. Definitely a great presentation. It brought me back to the days where, I was stuck in the lab for hours on end, up to probably days on end, waiting for my sims to finish when I was in college. So it's definitely good to see that, with the advancements in CPU power and all that other stuff, it's a lot more possible on a smaller, or on like not so supercomputery scale. So.
Yeah, it's definitely better today than it used to be. Yeah, but yeah, absolutely happy to join you guys, and looking forward to if you have any additional questions or maybe something you didn't want to share here or something you think of in the future. Definitely feel free to reach out to us, and we're more than happy to give you an answer.
All right, then. Again, thank you very much, and thank you all for being here. Next week, definitely stay tuned for a possible Halloween special, even though it's a couple days before Halloween. So we'll see you then. Have a great day, everybody, and we're out.